I will begin. That class made for odd alliances. It was me and like 3 of my friends from physics, and let's see. I would say 3 of us were Christians. The other guy, he's new agey in his background, and there was also a Muslim girl in the class, and we were the 5 who like refused to accept evolution in that class. It was like us versus this crowd of like 35 know-it-all engineers who argued by authority that evolution was the thing. It was a lot of fun. You might wonder, how did a class on the rise of modern science become an evolution debate? But it did. So my favorite moment in that class, though, by far, it was about maybe like 2 classes in or so, and my friend, who I refer to as Crazy Paul, he was talking about, I think we were talking about how the Newtonian revolution in physics had led to the industrial age, and like we're talking about how man is able to control nature, and we were just like, dude, you're wrong. Like, it's not how it works. We do not have control of nature, you moron. Like, you are wrong, sir. But anyway, so in the midst of that, somehow Paul was making an argument that involved Nikola Tesla, because this is one of Paul's heroes. Do you guys know who Nikola Tesla is? Good. See, because Paul inadvertently used Nikola Tesla in his argument, at which point the professor, all right, mind you, a graduate student, a man whose professed specialty is science history, all right? More than that, science history in the 20th century too. So he was even supposedly an expert about, or becoming an expert about, this period of time, recent science history. Not talking about ancient Greek dude or anything like that. And he's like, I'd like to refute your argument, but I don't know who this Tesla is you mentioned. Paul was so upset. Paul was just, he was holding a pen like this, and he just went, ah, just like that. I mean, he just threw that pen, like it would, just like that. And then Paul looks back at that moment, and he's like, that is the moment we should have dropped that class. And I don't know, I'm glad we didn't, because it was fun. But did he win the debate?
Was it like a big class debate, like a for a grade debate?
Well, can you have a debate with someone who doesn't know anything? I don't know, like
100%.
It was so disappointing for us too, because like I was thinking, this is great, I'm gonna take this history class, but even though it's a history class, I'm gonna learn about all this science history. I'm gonna, it's gonna be great. I'm gonna really, no, the opposite. No, no. Anyway, in my defense, I wanted to take ergonomics because, oh no, that was another story. I never got to take the the non-required fluffy fill out your major to keep the other departments alive class. That I wanted to, Like I wanted to take ergonomics. I got funneled into the psychology of, what was it? Industrial and organizational psychology.
That sounds awful.
It was truly awful. But the weird thing was, like, the professor I had in there was definitely one of the top 10 lecturers I had in any class. I wrote in his course evaluation, like, you're a fantastic professor. Your lecture is amazing. I just wish you were talking about anything else. So, which is, in retrospect, like, I mean, it's a compliment, yeah, but on the other hand, it's very disheartening. Because, I mean, he must love that stuff, right? He's his chosen profession, I guess.
Is that what he told him? He actually told him that?
Not in course evaluation.
Oh.
As we always do, the cowardly after the fact, we never actually go tell a professor something like that to his face. Of course not. Right. But anyway. I mean, some people would.
Yeah.
But
Sasserwood.
Sasserwood?
Yeah.
Comes with a name, right?
Exactly.
Okay. Well, I will begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. I thank you for these students. Just ask that you bless our work today. Help us to glorify you, what we do, and to learn some math. In your name I pray, Lord Jesus. Amen. All right, so, guys have any questions about anything particular? Yep.
I had a question on the business.
Uh-huh.
It was one where you had to use arctan and series, and I was looking through my notes and I was still confused. I'll take the integral like the summation after you work it out.
Arctan and
Problem 97.
sure. So that one. Oh yeah, that just says to find the power series for inverse tangent, right? So I'll do one like that. So just we did this before, but I'll do it again. So suppose you got f of x is inverse tangent of x. All right. Then we notice that df dx is 1 over 1 plus x squared. But this is the geometric sum, right? So we can rewrite this as the sum n equals 0 to infinity of minus x squared to the n. But this simplifies to the sum n equals 0 to infinity of minus 1 to the n, x to the 2n. All right? And OK, great. So that's the derivative, the power series for the derivative. What's the function? Well, integrate. So f of x is equal to some constant, I don't know what it is yet, plus the integral of this term by term. What's the term by term integral of that? Well, sum n equals 0 to infinity of minus 1 to the n divided by 2n plus 1, x to the 2n plus 1. So what I've done to go from here to here is to integrate. And I've used the term by term rule, right? The integral of a series is the series of the integrals where you just integrate each power function by its lonesome. It is important that it is a power series before you apply this result. If you try to apply the term by term integration theorem to things that are not power series, it will not go well for you. I know this seems like kind of like a, well, when would I ever do that? You will do it. I've already helped some of you doing it. So then what? Well, this constant, we don't want it, right? So we figure out what the constant is by plugging in 0. So f of 0 is c plus this. What's the lowest order term in that? Look at it. N equals 0 is the lowest order term. What happens when you put n equals 0 into that formula? You get x, right? So this starts with an x. I don't really care what this number is. It starts with an x. What happens when you plug 0 into x? Well, it's 0, right? What's the next thing? X cubed, then x to the 5th, then x to the 7th, 9th, so forth. Those are all odd powers of x when you plug in 0. They're vanishing. So this whole expression becomes c plus 0. That's equal to, it has to be equal to the inverse tangent of 0 because that's what we're trying to find the power series for, right? What's the inverse tangent of 0? Well, it is 0, right? So therefore, it's very anticlimactic, but the constant is 0. It was 0 last time we found it. It's still 0. That's good. It'd be sad if we came back to math like 3 weeks later. 2 weeks later? 2 weeks. 2 weeks. 2 weeks later, and we found out that it changed. Like, that would be annoying. But fortunately, math is not postmodern. It does not care about your story. Using a more authentic voice to communicate it does not change its truth value. Let's see here, 2n plus 1, or any of that stuff. I don't know. You guys can explain all that to me. So there you go. That's the power series for inverse tangent. Yes, sir?
Wait, can you explain why that summation goes to 0?
Because this is, what is this when you write it out? Well, it's x put in n equal to 0 gives me x. Put n equals 1, I get minus 1 over 3, minus 1/3 x cubed, plus 1/5 x to the 5th, and so forth. So when I plug 0 into that, it's the 0 series. Yeah. This doesn't always happen. There are places where the constant ends up being something interesting, right? It can happen. But OK, so this doesn't solve your problem yet, right? Because the problem is about inverse tangent of what? 7 something, right? So what I suggest, though, is we add this to our list of trophies, all right? So let's put this in our examples. So for today, I guess number 1. This is kind of an odd first example, but we have that the inverse tangent, and I'm going to change the letter. Inverse tangent of u is the sum n equals 0 to infinity of minus 1 to the n over 2n plus 1 u to the 2n plus 1. So the homework problem you're asking about, number 97, all you have to do is set u equal to 7x cubed, right? So like example 2, I won't do exactly your example. I'll do something like pretty similar, but you know, if I have inverse tangent of, oh, I don't know, 13 x squared, that's kind of obnoxious. Well, that would be the sum n equals 0 to infinity of minus 1 to the n divided by 2n plus 1, parentheses, 13 x squared to the 2n plus 1. Now this wouldn't be the answer, right? Because at the moment, this is not a power series. Not yet. I need to do the algebra and write it as constants times powers. All right, so like, you know, power functions. So this would be the sum, one step really though, n equals 0 to infinity of minus 1 to the n. This is giving me 13 to the 2n plus 1 divided by 2n plus 1. And then this gives me what? X squared. What is x squared to the 2n plus 1? It's x to the 4n plus 2, because we multiply exponents, right? So we have x to the 4n plus 2, and that would be the power series, well, the Maclaurin series for inverse tangent of 13x squared. Does that make sense? Yep.
So if we just memorize that, we can just use it for...
Yes. Yeah. Yeah. I think that one's probably worth memorizing. I don't know. I don't memorize that one. I just know how to derive it because it's like too much work to memorize everything. But either memorize or derive, yeah.
So for the homework, can we just write the equivalent of...
Yeah, you can say in class we showed that inverse tangent of u is that, and then so substitute, sure.
Okay.
It would be better for you in the homework if you just worked out what I just did here, because working this out will make you remember it.
Yep.
In my experience, if I work it out about 3 times, I remember things. Yeah.
When you went from 1 plus 1 over 1 plus x squared to the sum from 0 to infinity
Uh-huh.
of n negative x squared,
Yeah.
how did you go from one to the other?
This is the geometric series. And this geometric series said this: c over 1 minus r is equal to the summation n equals 0 to infinity of c r to the n, or the terms and conditions here, provided what? The absolute value of r is less than 1. Now, I don't fuss over like interval of convergence and radius of convergence in the midst of the later problems, right? That's the first part of your homework. It's all about what's the domain, what's the domain, what's the domain, right? So one thing at a time. So I started with the domain question, which I don't think is that interesting, frankly. All right, like comparatively speaking, to me, this is way more interesting than the domain question. How do you find the power series? To me, this is what's interesting. Because when you can apply this to things, right? Like if you're working with a, you know, if you're working with some physical problem and you end up finding that whatever you're modeling depends on inverse tangent of 13x squared, well then if you want to just like, and your x is small, well then I can approximate inverse tangent of 13x squared. That's approximately equal to 13x squared minus 1/3 of 13x squared cubed plus dot 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 dot, right? So like to a very good approximation, if x is close to 0, these first 2 terms, well if you just want, if x is really close to 0, 13x squared is a pretty good approximation for inverse tangent of 13x squared. So this is a method to get, you know, approximations of complicated functions to arbitrary order by taking polynomials as large as you need. Now that as large as you need is a more sophisticated question to pin down precisely, and we'll do more of that. But I think first we should just settle how do you find the power series, right? The more technical question is how do you find the power series to be accurate within a certain precision? Like that's a harder question that I don't typically hold students' feet to the fire on tests on. Yeah.
So if you didn't use formula, like the answer right there,
Yeah.
and you just like went straight and tried to,
Oh no.
it would take a while.
Yeah, you don't do that. You don't want to. I know what you're going. You're like, well, you told me last time there's this thing called Taylor's theorem, right? And Taylor's theorem said, what did it say? You know Taylor, right? Like, if you don't know this, there's great shame. What did it say?
What? Oh, you're asking me? Oh, hold on.
No, you can't look back. You got to know
Look
this.
at A smooth.
I'm asking you what your name. I'm asking your namesake. You can't look that up. You got to just tell me.
Taylor's theorem is a theorem that Taylor wrote.
Taylor's theorem is a theorem. That's what you wrote. So f of x is equal to the sum n equals 0 to
I'm not incorrect.
n equals 0 to infinity of the nth derivative of a over n factorial times x minus a to the power n, right?
Yeah, that's right. Yeah.
So what this is, very good. What this is f of a plus f prime of a times x minus a plus 1/2 f prime prime of a times x minus a squared plus 1 over 3 factorial f prime 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 of a times x minus a cubed, and so forth. All right? This is a weapon of last resort. You don't want to do this if you can avoid it, because to do that is to differentiate a lot, right? And if the function's complicated, like this one, the first derivative doesn't hurt that much, right? But how about the second derivative? Because the first derivative brings you to, 26x over 1 plus 169x to the fourth. Great. Now differentiate again, quotient rule. Differentiate again. Ugh. Uglier quotient rule. Differentiate again. Still uglier quotient rule. And it just keeps like this. To get these first two terms, that's the 6th power. I would have to do 6 derivatives to generate these coefficients, only to find out that four of the coefficients were 0, right? So you absolutely must not use Taylor's theorem without thinking. Like, Taylor's theorem is a weapon of last resort. It's kind of like the integral test for convergence and divergence, right? If you find yourself needing to use the integral test, you should have exhausted all your other options, right? So, anyway, other questions? Let me remind you the other examples we know. Last time we learned that e to the u is the sum n equals 0 to infinity of u to the n over n factorial. We learned that hyperbolic cosine of u is the sum, let's say j equals 0 to infinity of 1 over 2j factorial u to the 2j. We learned that hyperbolic sine of u was the sum over odd powers, right? J equals 0 to infinity of 1 over 2j plus 1 factorial u to the 2j plus 1. And we learned that cosine of u was the sum minus 1 to the j over 2j factorial, j equals 0 to infinity of u to the 2j. Now, you probably have these in your notes already, so like you don't have to write them down again right now if you don't want to. It's all up to you. J equal to 0 to infinity minus 1 to the j. I probably have written them with x last time, right? But I think it's helpful to us to think about them in terms of another variable, because we're going to use these to make substitutions, right? And then, of course, the bedrock beneath that all, the geometric series, right? So I won't write that again, but we always keep an eye out for the geometric series. Is there another example we have? What else did we derive? A lot of people know about this one, right? The natural log of 1 plus u, what would that work out to? Do you guys remember? It was the sum n equals, I think it was 0 to infinity. I believe it was minus 1 to the n. I could be wrong about this, guys, so we'll have to check on me. U to the n, 2n plus 1. Was that it? Let me check on this. If I plug in 1, no, there's not 2n plus 1. It's just n. It's just n and n. That's what we got. I remember this because if I plug in 1, I get natural log of 2 on the left-hand side, and I get the alternating harmonic series on the right-hand side, which is what we derived. And it diverges when I plug in 0 because it becomes the, wait a minute. Whoa. No, that's not right. Just 1 over n, right?
It was alternating.
It was, well, I'm trying to remember.
That's the one you did on the number line.
Hey, listen, so I forgot. What do we do? Yeah, do it again, right? If you forget something like this, if you understand the geometric series technique, it's a simple thing to remember, right? Let's work it out right quick. F of x, oh man, this marker's garbage. Natural log of 1 plus x. So you differentiate that thing, I get df dx is 1 over 1 plus x, which is the sum n equals 0 to infinity of minus 1 to the n, x to the n, which then I integrate, and it gives me f of x is equal to a constant plus the sum minus 1 to the n over n plus 1. Aha! X to the n plus 1, n equals 0 to infinity. And then I plug in 0. What's 0 give me here? Natural log of 1, which is equal to 0, which is, c is 0 again here. So apparently, I'm supposed to have minus 1 to the n over n plus 1, u to the n plus 1. Okay, so we could write it that way. That's handy because you have some problems in your homework that are about natural log of 1 plus something, right? So you can either derive it like I just did, right? Or you can use it to make a substitution to do that kind of problem. Are we good? So I did this rigmarole earlier more slowly. I took like 10 minutes of class. I don't want to belabor it today. There's still a couple of weapons, if you will, that we haven't taken out and brandished about. You know, there's still some tricks up my sleeve that I need to share with you guys. Actually, quite a few about power series calculation. And some of these tricks really are just combining pre-calculus you don't know with power series stuff that you're learning. And some of you know the pre-calculus. Let me not be too, pessimistic. You know this pre-calculus that I'm going to use. So when it happens, you'll be like, oh, yeah, I know that. Let's see here. So like example 3. Let's start out kind of benign. How would you find the power series for 2 to the x? Now, so we can make Taylor happy, and we could just do Taylor's theorem directly, right? You can calculate derivatives of this all day long, right? What's the derivative of 2 to the x? We get what? Natural log of 2 times 2 to the x, right? What happens when you differentiate again? You get 2 natural logs 2, right? So the nth derivative of 2 to the x is natural log of 2 to the n power times 2 to the x. So the Maclaurin series for 2 to the x is easy enough to build, right? The derivative is natural log of 2 to the n power. So then, therefore, we find 2 to the x is equal to the sum, n equals 0 to infinity, of natural log of 2 to the nth power divided by n factorial times x to the n. So there you go. There's the power series for 2 to the x. I didn't really do anything clever here, right? The clever way to derive this is to just take the exponential and manhandle it into this. So let me show you that. The other way to do this would be like this. I can take my 2 to the x, and I can rewrite it as e to the natural log of 2 to the x. In other words, it's e to the x log 2. So therefore, 2 to the x is equal to the sum, n equals 0 to infinity, of 1 over n factorial times x log 2 to the n. Here I'm just making a what? U equals to x log 2. So like my, formula 2, right? No differentiation, right? Just pre-calculus. But maybe pre-calculus that you haven't quite absorbed yet, right? I've shown you this trick somewhere before. I think I was finding like the, I was messing around with the half-life formula in an exponential. Someday I did that. I mean, you may have forgot. It's understandable. This class is not a sprint. It's a marathon, right? So this is one kind of small trick, right? Here's another. What if you wanted to, any questions before I? So here, there's not a big cost for using Taylor's theorem, right? You've been equally fine to use Taylor's theorem here, not a big deal. And that's probably true for the next example as well. Well, no. Not the case. Example 4. How about this? What if you want to find the Maclaurin series for sine of x plus x squared? Let me write it this way. The sum n equals 0 to infinity of Cn x to the n. Like, find the coefficients. That's our goal, is to expand this function as a Maclaurin series. Why would you not want to do just direct application of Taylor's theorem? What would that involve? Chain rule. Yeah, chain rule. The first step is chain rule. What's the second step? Chain rule paired with product rule. What's the third step? Yet more product rules. Product rules upon product rules upon product rules. It's quite horrible. So how would you attack something like this? Let me show you. So what I would do is I would remember that I know trigonometry. And so I know that this is sine of x times the cosine of x squared plus the cosine of x times the sine of x squared. Now I may have to give up on my dream here of finding the full series. That might be a little bit above our pay grade. Maybe it's too hard. But let's see if we can find the first bunch of terms at least, all right? So then what? Do we know how to find the Maclaurin series for sine and cosine and sine of x squared, cosine of x squared? What would you do? Let's try to calculate the series to some particular order. What order do you guys want to aim for? Let's say order 6. Does that seem reasonable? I may regret that. Order 4. Let's go for order 4. Let's up to order 4. So by that I mean up to terms involving x to the 4th. So what this means is that gives me license to ignore things that are going to give me, say, order x to the 5th or x to the 6th, things like that. I haven't talked to you guys about this yet, but how do you do these kind of calculations? Like, can you multiply series? Is that a meaningful thing? The answer is yes. How do you do it? How do you multiply series? Carefully? That's a good answer. but the answer is pretty much the same way you did with polynomials. I could define it carefully. There's a way of carefully defining product series, and maybe I should do that. But rather than doing that, let me just go ahead and show you how it works. So, and the way it works is just what you'd expect, okay? So sine of x is x minus 1/3 x cubed plus dot 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 dot. The plus, what's the next thing in the plus dot 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 dot? The next thing is minus 1 over 120 x to the 5th. That's the next term in the Maclaurin series for sine. So we don't care about that because we're working order 4. Cosine of x squared. Well, that is 1 minus 1/2 of x squared squared. Right? So let me just write that as x to the 4th like a civilized human being. There we go. So here I'm making the u equals x squared substitution into the cosine series. Did you guys follow me? What's the Maclaurin series for cosine? So this is literally that. All right. Cosine, well, this is plus what? Plus 1 minus 1/2 x squared plus 1 over 4 factorial is 24. So 24x to the 4th. The next term past that is 1 over 6 factorial minus 1 over 6 factorial x to the 6th. That's too big for our current considerations, because I had the good sense to decide just to do order 4. I may still regret that, but anyway, here we are. Sine of x squared, well, that starts with x squared. And then the next term is minus, well, dot, dot, dot. See, the next missing term would be 1 over 6 x squared cubed, which is 1 over 6 x to the 6th. So we're not investigating that order yet. Yeah.
In that first sine series, you have a 1/3 on your x cubed term, so that's supposed to be 1/6.
Oh, yes. No, sorry. Yeah, thank you. Yeah. And did I go far enough? I said, oh yeah, order 4, so I don't need the x to the 5th term. All right. In fact, in retrospect, you watch for this kind of thing, right? In retrospect, did I need this? I didn't, right? Because when you multiply this out, that gives you x to the 6th, which we don't care about. So actually, I could have neglected that term and not lost anything. But as a general point of order, I try to write a little bit more than I need just to be sure I'm not missing something, okay? And then you multiply out. And the way I do it is I do it order by order. So I look across what I'm doing, and I look for everything that's a constant. Everything that's constant as my starting point. Is there a constant in all this? Where is it? Oh, yes, but this 1 is forced to multiply this over here, right? And everything here has x squared or bigger in it. So there's no constant. Right? That makes sense, because if this is f of x, right? What is f of 0? It's sine of 0, which is 0, right? And that is the meaning of the constant. The constant is the value of the function at 0 when we're calculating the Maclaurin series. So the constant should be 0. That checks. How about, oh man, how about linear terms? Yowzers. Well, let's just multiply it out here. So what I got is x from this times that. Is there any other way to get a linear term? I mean, that's it, right? How about quadratic? Well, x times, that's x to the 5th. This gives me x cubed. That's not quadratic. Oh, look, it's just this one right here. 1 times x squared, so plus x squared. All right. Then what's next? What next would be x cubed, right? Where are the cubic terms coming from? So we've got this times this, right? It gives me minus 1/6 x cubed. And I think that's it for here, right? Because we think about multiplying this out, we think about foiling it out. The only way to get an x cubed from that first product is just the product of minus 1/6 x cubed and the 1. How about over there? Is there any x cubed terms over here? I've got this 1 times x squared. We already took care of that. I've got x squared times x squared. That's x to the... No, that's it. There's no cubic term over there. That's the unique cubic term here. What comes next? X to the 4th. What are my x to the 4th terms? Well, here, nothing, right? Because this gives me x to the 5th. This gives me x cubed. There's no... Right? In fact, you can streamline your thinking if you stop and take a step and take stock of what you're looking at. This function, sine of x times cosine of x squared, is it even or odd? Think about it. Sine is odd, cosine is even, cosine of x squared is still even. So this is an odd function. That means it's only going to contribute odd terms to the power series. Because odd functions have odd power series, odd Maclaurin series. So like this contributed this x and this x cubed. It's not going to contribute x squareds. This over here, on the other hand, is an even function because while sine is odd, sine of x squared is even because x squared is even. So if you check it, this is an even function. It's going to contribute even terms, as it has been. In particular, this x squared term came from here, and also the x to the 4th is going to come from over here, minus 1/2 x to the 4th. And I think that's it for here, right? Because I don't multiply this times that. That's not nonsense, right? And so there you go. That is the power series for sine of x plus x squared to 4th order. This is kind of a hard example to start multiplication of power series with. My apologies. I kind of stumbled into it. I should have done something easier with you guys first, yeah.
Is there an easier way to know like what order to go to, or just like?
It has to be given to you. So that's why I stated it, up to order 4.
So if
yeah.
it was on a test, you'd be like up to order 4.
Order 4. And I mean, other examples, I ask for the full thing. You know, I'll just say find the power series. Yeah.
How would you determining like the x minus 1/6 x cubed? Are those like the derivative?
I'm just reading the power series for sine over here. So like the other thing I would do on my sheet of remembrance is write out the first 3 terms for this, which in this case is u minus 1/6 u cubed plus 1 over 120 u to the 5th plus dot 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 dot. So those are the first 3 terms in the Maclaurin series for sine. Another question? Or yeah.
So where you have cosine of x squared right there.
Uh-oh. Yeah?
No, it's
Okay.
not a problem. It's just so you're basically plugging that into where you have cosine u.
Right.
Right. So how do you know what functions of x you can plug in and which ones you can't?
Oh, I don't know one you can't. I mean, that's an interesting question. When does this fail? I don't know if I have an example for that.
So like when you have sine of x plus x squared, can you plug that into your sine series?
Ah, yes, but there are terms and conditions. And I think that'll work here. So your point is, couldn't you do it this way? So let this be u, right? And so this is u minus 1/3 u cubed. I keep doing that. 1/6 u cubed, right? So then you've got yourself what? X plus x squared, right? Minus 1/6 what? X plus x squared cubed. Which is fine. I mean, this is legit. But you got to be careful. Because you got to think about, when I get to that next term, does it have things in it that I care about? What's the next thing? 1 over 120 x plus x squared to the 5th power. Yeah? So how do I, what is the cube of x plus x squared? I mean, we can do that. 1, 1, 1, 1, 1, 2, 1, 3, 3, 1. So x plus x squared cubed is x cubed plus 3x squared times x squared plus 3x times x to the 4th plus x to the 6th. Using the binomial theorem, but there's a sixth in front of that mess. That's x to the fourth, right? Plus 3x to the fifth, plus x to the sixth. Now, if I was sticking with my principle of maximal laziness, I wouldn't be writing some of these terms down, right? The question I have to ask, though, is, the question you have to think about is, the next term we're not really expanding. What kind of orders does it have in it? And what's the pattern for things past that? See, so this right here, what's the lowest order? It's not fifth. Oh, wait a minute. No, I don't think it's fifth, though, because, well, yes, you're right, it's fifth. Fifth order is 5. And you see that from this x, when I take x, 1 plus something to the fifth power, there is going to be one term in that which is from multiplying the x times x times x times x times x times x 5 times, right? Which gives us x to the fifth. That's the lowest possible order in that. Everything past that is higher order. What's the highest order in this? The highest order in this one is like x to the 10th. That comes from x squared multiplied by itself 5-fold times. So I think this has everything in it up to order 5. Because the terms past that are higher order. So great. Is it what we got? Well, this is x plus x squared, what? Minus 1/6 x cubed. Great. And then what's next? Where is it? Oh, so 3/6 is a half. Oh, good. Well, it would be disturbing if we found different answers different ways, right? Yes, you can. Almost anything that you can think of logically, it will be true. I don't know how to break these methods. It's kind of like the integration technique. So like we avoid complex variables, but the truth of the matter is if you chase down the square roots of negative numbers and treat them logically, that stuff will work too. Okay, so let me try a more benign example. Let me show you where this goes wrong. Okay, let me show you why you don't why that this is especially friendly for the idea you just had, Caleb, because it's x plus x squared. When it's a number, it gets worse. So example 5, if something like f of x equals to sine of, let's say, 2x plus 3. Suppose you want to find the Maclaurin series for this. So if we used your idea directly, and I don't discourage it, you know, well, you'd have 2x plus 3, right? Minus 1 over 3 factorial times 2x plus 3 cubed, plus 1 over 5 factorial times 2x plus 3 to the 5th, right? And what's the pesky thing about this? Why don't we want to do this? The reason we don't want to do this is every term contributes to constant order. See, because there's a constant in every power. And so while it's true, it's absolutely obnoxious to like try to sort through order by order and pull those all together to find the answer. There are other ways to go about solving this problem. And the other ways are, you know, to use Taylor's theorem directly, right? Because you could differentiate this, right? You guys could differentiate this. It wouldn't be that big a deal. So surely, I admit, you could use Taylor's theorem directly here. But what I tend to do for this problem is to do what I did over there, but it's much easier. See, because it'll give you a nicer answer too. See, check this out. So this is what? Sine of 2x, cosine of 3, plus the cosine of 2x sine of 3. Now I can use the Maclaurin series with the substitution, right? I make u equal to 2x for both of these, right? So here's how it goes. Take that cosine 3, leave it out front. You got yourself a sum, j equals 0 to infinity, all right? Minus 1 to the j over 2j plus 1, factorial, parentheses, 2x to the 2j plus 1. So far, what I did was I just applied our known Maclaurin series for sine, and I wrote those terms there, all right? And then I have plus what? Plus the sine of 3 times what? The sum, let's say j equals 0 to infinity, minus 1 to the j over 2j factorial 2x to the 2j. Because that's the cosine series, right? Now let's clean it up. What we have then is the sum, j equals 0 to infinity of minus 1 to the j times the cosine of 3 times 2 to the 2j plus 1 power divided by 2j plus 1 factorial x to the 2j plus 1 plus the sum j equals 0 to infinity of minus 1 to the j sine of 3 divided by 2j factorial, and I've still got a 2 to the power 2j up here, all times x to the 2j power. So this term right here was this one. And there you go. This is the Maclaurin series. And I didn't have to differentiate, right? But I do have to know my pre-calculus. I have to know the adding angles formula for sine to do this like nicely. Now I can answer, like let's ask a really slightly tricky question. Can you calculate? So here's an add-on. Calculate the 49th derivative at 0 for this f. And let's calculate the 50th derivative at 0. Can you do it? Man, I was trying to get the multiplication of series and division of series today, and I have not got there yet. I'm going to do it right after this example. I mean, we did some multiplication over here, but not as much as I'd like. The kind of multiplication we did in that example is important. Like that is like one of the skills that you want to acquire. That ability to like pick through, just find order by order what you want. That's an important calculational idea. Now, so here, the idea is simply this. If I tell you ax squared plus bx plus c is equal to 7x squared minus 11x plus 2, what are a, b, and c? I'll repeat it. I have 11x squared. I already forgot my polynomial. But my point to you is if I give you a quadratic and I tell you that the coefficients are a, b, and c, you know how to find them, right? What are you doing? You're comparing coefficients, right? So two polynomials are equal only if their coefficients are matching and they have the same order, right? Two power series are equal only if their coefficients are matching order by order, every single last one of them. So on the one hand, I have this wonderful formula. You can debate whether or not this is wonderful. But on the other hand, we have Taylor's beloved theorem, right? So right here. So this gives us a formula. Like, let's write it out. We have C, let's call it C50, right? C50, the coefficient of C50, on the one hand, it's the 50th derivative, evaluated by at 0 over 50 factorial, right? On the other hand, where is it here? Is it in this one? Is it in that one? Where is the x to the 50th term? It's even, right? So it's surely over here, and it's when j equals to what? How do you get x to the 50th here? Yeah, 25. X to the 50th for j equals to 25. So I put 25 minus 1 to 25 sine of 3. 2 to the 50 divided by, well, 50, right? Factorial. I believe. Yeah. And so therefore, the 50th derivative of this function evaluated at 0 is apparently 2 to the 50th minus 2 to the 50th times the sine of 3. Now, I do think that you guys could calculate that. Like if I, if I had a room full of sufficiently interested high school Calculus 1 students and I made this worth something to them, they could figure this out through successive differentiation and staring at it. Like you could do it. But this technique I'm showing you works for much uglier things. Yeah? What's C49? So we can look at the 49th derivative evaluated at 0 over 49 factorial, and that will be equal to, let's see, that's going to come from over here with j equals to what in this one? 24, right? So put j equal to 24 over there, and we get minus 1 to the 24 times the cosine of 3 times 2 to the, what, 49, right? Divided by, apparently, 49 factorial. So usually when I work these problems, the factorials on the bottom don't cancel. Typically, there's some kind of ugly factorial in these kind of problems. Not this one. Anyway, so therefore, the 49th derivative evaluated at 0 is 2 to the 49 times the cosine of 3. So there you go. All right, so let's work a multiplication of polynomials problem that's without end. All right, I mean multiplication of series problem. I want to work a multiplication series problem that we can do to the bitter end. Okay, you guys ready? First of all, any questions about this? There are some problems like this in the homework, so I wanted to make sure I threw one at you. All right, well, let's keep going on. That was example 5. Example 6. Yeah, I guess under here. Example 6. So you guys try this out. What's 1 plus x times the series 1 minus x squared plus, 1 minus x rather, plus x squared minus x cubed. Oh, I'm sorry. I still did it wrong. I'll get it right eventually. 1 minus x times 1 plus x squared plus x cubed plus x to the 4th plus dot 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 dot. How would you multiply? This is kind of a silly example of series multiplication. Let's do that one. A slightly less but equally silly example would be something like this. We have x minus 1/6 x cubed plus dot 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 times 1 minus 1/2 x squared plus 1 over 24 x to the 4th plus dot 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 dot. I guess I owe you one more term here. Minus 1 over 120 x to the 5th. So let's try to multiply these out, see if we can. So the second one, let's say we'll work to order order 5. The first one I want to work to arbitrary order, right? all the way. Are you guys rich? I mean, in other words, a similar question. Do you eat at Five Guys? So, no? Four guys? Yeah. We used to eat at Five Guys, and then I went back and I was like, what happened? Like all of a sudden, it just seems like amazingly expensive. I do have 5 children, but there's no kids meal there. Anyway, I digress. Yeah.
Did you mean one positive one or one?
No, I mean 1 minus x. So what happens here?
I mean, it's not plus, minus one.
Oh, yes, I'm sorry. That's a plus. Thank you. So the first, you say telescopes? Kind of. So like when I multiply through 1, I get, let's do it order by order. Constants, what do you got? 1, right? Then what? Order 1, what do you got? Plus x, minus x, right? That's all the order 1 terms. How about order 2? Plus x squared, minus x squared. And then what happens? Plus x cubed, minus x cubed. All right, so what's this? So we've multiplied this series by this polynomial, and what do we get? 1. So what does this mean? This means that 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus dot, 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 right? You already knew this. See? You guys shouldn't have needed to multiply, because if you know the geometric series, you should recognize what you're up against. See, because this is... I told you guys I'm going to monetize my channel in like math pranks. This is perhaps a math prank. I don't know. It's borders on it, but that's the geometric series. Of course, when you multiply that by 1 minus x, it works out to 1. It better, right? How about this next example? Can I erase the blue? I need to erase the blue. I guess I can work below here. So you guys tell me, what's the lowest order in this product? X, all right. And, oh, tell you what, for our convenience, let's put a 2 out here. 2x. What's next? X squared, possibly. So, but I think not, because I have x times, that gives me x, this gives me x cubed. So x cubed is next, actually. How many x cubes do I got? 2 times what? Times minus 1/2 x cubed. So this is from this times that, all right? And then what else do I have? This one, right? Times that, which gives me minus 1/6 x cubed, right? And I'm just keeping the 2 out front for my own nefarious purposes. And how about x to the 5th? What do we got there? You got your x times, so yeah, 1/24th, x to the 5th, right? And then the other one is what? So I would have this guy times this one, right? So that gives me plus 1 over 120 x to the 5th, right? And then I said we're just going to go to order 5, so that's all I owe you. How do these work out? What you got here? 2x, right? This looks like a net minus. You got what? Minus, I think it's minus, I don't know, 1 over 6 times 2x cubed, maybe?